Hello everyone. Today I will present an interesting and impactful work, the diffusion models as plug and play priors. This research explores how diffusion models, traditionally known for their success in generative tasks, can be transformed into modular and reusable components. This transformation enables their adaptation to a wide range of tasks without retraining, addressing a significant limitation in their current application. Throughout this presentation, I will discuss with you the motivation, core ideas, methodology, experiments, and implications of this innovative work. Generative models, such as the generative adversarial networks, variational autoencoders, and diffusion models have become central to advancements in artificial intelligence. These models achieve outstanding performance in generating realistic high-dimensional data, such as the images and the text. Among them, diffusion models stand out due to their ability to model complex data distributions with remarkable accuracy. However, despite their success, diffusion models are not without challenges. A key issue is their lack of flexibility. Adapting these models to new tasks or domains often requires retraining or fine-tuning, which is computationally expensive and time-consuming. This work addresses this limitation by asking a fundamental question: can diffusion models be made modular and reusable? If so, how can they be adapted to new tasks without retraining? The authors propose an elegant and practical solution to this challenge, which we'll explore in depth today. Let's talk about the motivation behind this research. Generative models, particularly diffusion models, are computationally intensive. Retraining or fine-tuning them for each new task demands significant resources, limiting their practical use. This raises a critical need for a method that enables these models to adapt to new tasks. The primary objective of this work is to transform diffusion models into reusable modules that can be combined with task-specific constraints. These constraints guide the model's output towards the requirements of the new task, eliminating the need for retraining. This approach is both resource efficient and highly versatile, paving the way for broader applications for diffusion models in artificial intelligence. The core idea of this work revolves around the three fundamental steps. First, a pre-trained diffusion model is used as a prior distribution, denoted as Px. This prior enables the general knowledge learned during the training phase of the model. Second, task-specific constraints, represented as CXY, are introduced. These constraints are mathematical functions that define the specific requirements of the new task. For example, in image generation, constraints can enforce properties like symmetry or belonging to a specific class. Finally, the prior px and the constraints cxy are combined to approximate the posterior distribution px over y. This posterior represents the output that aligns with both the general knowledge of the model and the specific requirements of the task. Importantly, this process requires low retraining, making it very computationally efficient and flexible. And by doing so, we can solve the challenge. Diffusion models simulate a reverse process that starts with random noise and iteratively refines it into meaningful data. This process begins with xt, a point of pure noise, and progressively moves towards x0, the final data sample. Each refinement step is governed by Gaussian transitions, with parameters optimized during training. These transitions add structure and details to the data at each step. The strength of diffusion models lies in their ability to model fine-grained details, which is very crucial for tasks that demand high accuracy and realism. The reverse diffusion process forms the backbone of the proposed method, enabling the generation of data that adheres to specific constraints. Now, let's formalize the problem addressed by this research. We can start with a pre-trained diffusion model. And this model provides a prior distribution, Px. Alongside, we define a task-specific constraint, Cxy. And this constraint encodes the requirements of the tasks. The goal is to approximate the posterior distribution, Px over y, which combines the prior and the constraint. This allows us to generate data samples X that not only align with the general knowledge encoded in Px, but also satisfy the specific requirements imposed by Cx1. This formulation ensures that the model adapts to new tasks without retraining, preserving computational efficiency. To achieve the desired posterior distribution, the authors define a free energy function, the big F. And the formulation is just shown like this. This function combines three terms. The log Px represents the prior from the diffusion model. The log Cxy encodes the task-specific constraints, and the log Qx approximates the posterior distribution. The optimization process minimizes this free energy function by using gradient descent. This iterative process ensures that the generated samples align with both the prior and the task-specific constraints, achieving the desired adaptation without additional training. algorithm proposed by the authors follows a clear and straightforward process. The first step is to initialize X with random noise, and the noise is drawn from a Gaussian distribution. In each iteration, update X by combining gradients from two components. The denoising term, which aligns X with the diffusion prior. The constraint term, which ensures X satisfies the task-specific requirements. And the third step is to repeat the process until convergence. After sufficient iteration, the refined X represents the final output that satisfies both the prior and the constraint. This iterative refinement forms the basis of adapting the diffusion model to new tasks. The authors applied this framework to three diverse applications to demonstrate its versatility. The first application is conditional image generation. In this application, we need to generate images with specific attributes, such as digits with defined properties or faces with desired features. And in the second application is semantic image segmentation. In this application, we need to label pixels in images based on categories, such as non-cover classification. The third application is the optimization tasks. By solving combinatorial problems like the traveling salesman problem using the diffusion model as a prior. These applications show the wide-ranging potential of treating diffusion models as plug and play priors. Let's explore each of these applications in detail. Conditional image generation is one of the most intuitive applications of this framework. In this application, the authors explore two distinct tasks. First, generating mixed digits with specific properties, such as thinness, symmetry, or belonging to a particular class. This demonstrates that how the model can adhere to simple, well-defined constraints. Second, generating more complex face images with specific attributes, such as smiling, blonde hair, or the absence of a bird. This task highlights the framework's ability to handle more intricate constraints while maintaining the realism of the generated images. The flexibility of this approach stems from its capacity to combine general priors with task-specific constraints, making it adaptable to a wide range of generative tasks. Here we show the results of the mixed generation tasks. The figure shows the results for mixed digit generation. On the left, you can see examples of digits generated with varying thickness, showing the model's ability to enforce thin or thick attributes. In the center, we observe digits generated with a symmetry and symmetry constraints. On the right, the model generates digits belonging to a specific class. In this case, the digit 3, So we can see that it generates different types of the 3, and both these written digit 3 belong to 3, this class. These examples clearly illustrate how the imposed constraints guide the model to produce outputs and satisfy the desired properties while maintaining the general quality and realism of the diffusion model prior. This demonstrates the robustness and precision of the framework when applied to straightforward generative tasks, just like the MNIST. The second task within conditional image generation focuses on generating face images with specific attributes, a much more complex and challenging dataset compared to MNIST. For this task, the authors utilize the two of the shelf components. The first is a pre-trained DDPM trained on FFHQ 256 dataset as the diffusion model prior. And the second component is a ResLet 18 classifier trained on the syllable A dataset to impose the attribute-specific constraints. For instance, the classifier could guide the diffusion model to generate faces that are smiling, have blonde hair, or lack a beard. The key advantage is here to generate faces that are smiling, have blonde hair, or lack a beard. The key advantage here is that both components, the prior and the classifier, are independently trained. This modularity eliminates the need for additional fine-tuning or retraining, highlights the practicality of this approach for real-world application. Here we can show the results of the conditional face generation. In the first row, you can see faces generated with attributes such as smiling, wearing glasses, or having high cheekbones. These attributes were imposed using the ResLet 18 classifier, while the diffusion prior ensures that the generated images remain realistic and high quality. The second row shows the same faces after additional post-processing to remove noise and sharpen the output. This step enhances the visual quality and ensures that the final images are polished and aligned with the specific constraints. Overall, this demonstrates how diffusion models combined with task-specific constraints can produce detailed and realistic outputs, even for complex datasets such as faces. The second application of this framework is semantical segmentation, which involves labeling each pixel in an image based on its category. For instance, in the context of land cover classification, each pixel might correspond to a specific type of terrain, such as water, vegetation, or urban areas. The authors apply this method to EnviroAtlas dataset, which contains land cover labels for diverse geographic regions. This task is particularly challenging because the dataset includes regions with vastly different distributions, urban areas, forests, and arid landscapes, for example. To address this, The method combines weak labels, rough high-level guidance with the diffusion prior, which refines the segmentation output and improves its accuracy. This approach highlights the adaptability of diffusion models in handling tasks that involve complex structured outputs. Here we present segmentation results across 3 different regions: Johann, Austin, and Felix. Each row illustrates the process, starting with the input image, followed by weak labels, the inferred segmentation from the model, and the ground truth. Despite the significant variation in geographical characteristics, Durham being more urban, Austin more mixed, and Felix predominantly aerial, the model achieves high-quality segmentations that closely match the ground truth. These results demonstrate not only the effectiveness of the diffusion prior in refining weak labels, but also its ability to generalize across different domains. This capability is crucial for practical applications such as remote sensing and land cover analysis, where data from diverse regions must be interpreted accurately. The third application demonstrates the use of diffusion models to solve combinatorial problems, specifically for traveling salesman problem. In TSP, the objective is to find the shortest possible route that visits all nodes exactly once and returns to the starting point. Traditional solvers for TSP often rely on discrete optimization or neural models trained with reinforcement learning, which can be computationally expensive or limited in scalability. This work takes a novel approach by encoding the adjacency matrix of the graph as a visual representation, a 64 times 64 image, and using the diffusion model as a prior to iteratively refine the solution. This combination of a visual representation and a generative model opens new possibilities for solving complex combinatorial problems efficiently and effectively. To leverage the capabilities of diffusion models, the adjacency matrix of the graph is transformed into a visual representation. In this representation, nodes are depicted as small dots, and edges collecting the nodes are shown as line segments. The intensity of these segments corresponds to the adjacency values, providing a structured image-like input. The image-based representation enables the diffusion model to utilize its vision-based inductive bias, mimicking the human intuition in solving special problems such as TSP. This approach highlights the versatility of generative models when applied to tasks traditionally handled by discrete optimization methods. The solution process involves 3 main steps. The first step is to encode the graph as an image and pass it into the diffusion model. The second step is to use a gradient-based updates to refine the adjacent matrix iteratively. align it with a learned diffusion prior and reducing noise. The third step is to extract a tool from the refined adjacent matrix and apply a simple two-opt heuristic to remove crossing edges and improve precision. This iterative process combines the generative capabilities of the diffusion model with lightweight optimization heuristics, ensuring both efficiency and accuracy in the final solution. Here we show the TSP results in two tables. The right table summarizes the performance of the proposed method on TSP instances with 50 and 100 nodes. The result shows that the method consistently produces near optimal solutions with an average gap of less than 1% from the true optimum. Additionally, the approach is computationally efficient compared to baseline methods such as beam search with neural solver, highlighting its practical utility for large-scale problems. In addition, the proposed method also consistently outperforms the baselines across different graphs. We can see from the left table. Here we show some visualization of the results. This figure shows an example of the TSP problem. The figure provides visualizations of TSP tools generated by the diffusion model. In the top row, the initial tools capture the overall structure of the optimal solution, but include imperfections like crossing edges. The bottom row shows the refined tools after applying the two-opt heuristic, which removes these crossings and ensures greater accuracy. This demonstrates how the combination of diffusion priors and heuristic refinement produces high-quality solutions that align with the optimal results. Despite its effectiveness, the proposed method faces two main challenges. The inference process remains computationally intensive, requiring multiple iterations for refinement. The performance is sensitive to the design of task-specific constraints. Poorly defined constraints can lead to suboptimal results, emphasizing the need for careful engineering or learning of these constraints. Addressing these challenges will be key to making this approach even more practical and scalable. This work provides several exciting directions for future research. The first is to develop faster inference techniques. Reducing the computational cost of inference will be significant for scaling this approach to larger datasets and real-world applications. The second is to explore combinatorial search problems. The ability of diffusion models to reason over uncertain hypotheses makes them well suited for generating candidate solutions in combinatorial tests. The third is to expand puzzle-solving paradigm. By mimicking human-like reasoning, diffusion models can tackle a broader range of complex problems, potentially provides new methods in the areas such as logistic planning and optimization. In conclusion, this work demonstrates how diffusion model can be transformed into modular plug-and-play components, enabling task-specific adaptations without retraining. By bridging generative modeling and optimization, this framework provides new directions for research and practical applications. Okay, that's all for today's presentation. Thank you.